We'll continue these exercises where we're looking for critical numbers, intervals on which functions are increasing or decreasing, relative extrema, and then to verify with the calculator. I'll do the odds. You should do the same process with the evens to make sure that you learn this, and the more you practice, the better it is. 29. X plus 2. Sorry, we have f of x equals x plus 2 to the 2/3. First derivative is 2/3 x plus 2 to the negative 1/3. Now when we rewrite this, we end up with 2 over 3 times x plus 2 to the 1/3 power, and this is another example of where this is the derivative, but f prime of x not equal to 0 is never equal to 0. There is one value, f prime of x does not exist at x equals -2, and so -2 is our only critical value. Now we have to go back to check to make sure that the function exists at -2. So we plug in -2, -2 plus 2 is 0, and 0 to the 2/3 power is still 0. So the function exists there, but the derivative does not, so that is a critical number. We could either have a sharp turn or a vertical tangent at that point. So we're going to make our number line and see x equals -2. We're working with f prime of x. So we'll choose a value to the left, -3, a value to the right, 0. We plug them into the derivative. For -3, -3 plus 2 is -1, to the 1/3 is -1, times 3 is negative, so that will be negative. Plugging in 0, we get 2 to the 1/3, that's positive, times 3 is positive. So in this case we have what appears to be a relative minimum here. Function is decreasing and then it's increasing, and the function increases from -2 to infinity, decreases from -infinity to -2. There is a relative min at -2, and what would the value? -2, we have to go back to the original function for that. Plugging in -2, that's going to give us 0. And so it seems that we've answered all the questions. We have the critical numbers, we have the intervals on which it's increasing, decreasing. We use the first derivative test, the change in derivative from negative to positive, to indicate that there is a relative min at x equals -2. We plug -2 back into the original function to get the y coordinate that goes with that. Alright, we'll plug this into the graphing calculator and see what we get. Alright, so our function is x plus 2 to the... Now, whenever we put a rational exponent into the calculator, we always have to put it in parentheses. X plus 2 to the 2/3. And that's all there was. So we're going to graph this, and we see we do indeed get a sharp turn at x equals -2, y equals 0. The function is decreasing up to that point and increasing after that point. So I'll take a picture of this and we'll go on to the next problem. Alright, number 31. Now, number 31 is an interesting problem because 31 involves an absolute value, a linear absolute value. And in calculus, whenever I see linear absolute value functions, I think graphically. So if you can graph this function, you're going to be much better off, and I mean without a calculator. So let's think about function transformations for a second. First of all, we have f of x is equal to 5 minus absolute value of x minus 5. Alright, so let's talk about this for a second. Absolute value of x, if you recall, just looks like that V shape. Absolute value of x minus 5 is going to be that V shape shifted 5 units to the right. Then negative will make this turn upside down. Negative absolute value of x minus 5. And then 5, adding 5 onto that, will shift the whole thing up. Something like this. 5 minus absolute value of x minus 5. And so, very briefly, that's what we're expecting. And when it's linear and it's absolute value, then we know that the slope is just whatever the slope of this is. Actually, we don't even need the slopes. We're not asked for the derivatives here. I would solve this completely using graphics. But again, you should be able to do something like this without first relying on your graphing calculator. So the moral of the story is, when I have linear functions, absolute value, in calculus, think graphically. Alright, so this tells me, looking at this, that the function is going to increase from negative infinity to positive 5. And it decreases from 5 to positive infinity. It has a relative maximum at x equals 5. And we can plug that in. We get 5 minus 5 is 0. At x equals 5, y equals 5. And I believe that's it. We'll call in the graphing calculator to verify what we did here. Alright, so we have 5 minus, to get to absolute value on the calculator, you go to math, then over to number. Option 1, absolute value. 5 minus absolute value of x minus 5, close parentheses, and we should be able to graph. Okay, I didn't zoom as I normally do. Zoom standard. There we go. And you can see that we get this maximum value up here at 5, comma 5, if we wanted to double check that. Maximum 4. Let's see, our left bound 0, our right bound 8, guess, and it's at 4.9999, which is basically 5, y equals 5. So that's good, and we will save a copy of this and go on to the next video. Now I just want to label up these diagrams, and I'll leave them in the final copy. We start with the parent function. We have shift right 5 units. Remember, when it's a negative inside the parentheses, that means you're going to shift to the right. Then we have flip, and then it's a shift up 5 units. And that completes the transformation. So hopefully you can learn to do that with absolute value linear equations. Alright, we'll go on to the next problems in the next video.